So I hope you realize not only that binary stars are cool, but that our understanding of the physics allows us to understand how we learn so much about them. As is the case with planets, if the inclination of the orbit is indeed zero, in the sense that the planets orbit in a plane that includes our line of sight, then something even more exciting is going to happen. Not only will we measure the full radial velocities, but halfway between those points where we measure the full radial velocities, just as with planets, one star will transit the other. And so there will be times during the history of transiting binary like this, where we see both stars. We can't resolve them, but we see both, and we see both sets of spectroscopic absorption lines. And then there will be times when we only see one of the two stars, or we see parts of one and all of the other. We see a non-trivial behavior of the light curve. And the light curve, as I promised with planets, will tell us things about the periods, the sizes, the temperatures of the two stars. And if we can combine this with Doppler measurements, we can learn a lot about the system. I want to spend some time looking at what we learned from a light curve, because I think it'll interest you, and I promised it when we did planets. Let's take a look at an eclipsing binary simulator. This is our eclipsing binary simulator. It has many features. I hope you'll play with it. Let's see what we can learn from an eclipsing binary. So here's our system over here on the left. We can change its parameters if we want, but I've set it up so we have star number 1 is a hot blue star. Its temperature is 7850 K. Its radius is 5 solar radii. Star number 2 is a smaller reddish star. It's only got 2.8 solar radii and a temperature of 6200 Kelvin. And I've chosen to view the system edge on. Let me show you what it looks like if we turn it around. This is our system. Notice that astronomers call inclination the angle that is 0 when you're seeing the system face on, and 90 when you're seeing it edge on. We're using a complementary notation for silly historical reasons, but I wanted you to know that other conventions exist. And we're imagining that we cannot resolve these two stars. So what we see is the combined light of both in our telescope, and we can make photometric measurements. We can measure the intensity. And over here on the right, we see the light curve. In other words, the time dependence of the combined intensity of the two stars. This will be a periodically changing, and we folded it back so we see a complete period, and then this red cursor shows us the current situation at any given instant, while on the left we can see the configuration of the system. And so as I start the animation, the stars are orbiting each other, and if I've stopped it at an interesting point, this is the point at which the red dim star is moving away from us, the blue more luminous star is moving towards us. So if we measured the Doppler shifts, this is the moment when we'd find maximal redshift in the spectral lines of the red star and maximal blue shift in the spectral lines of the blue star. And we could use that, for example, to measure their speeds. And that will be useful, of course, because we'll have some information from the Doppler shift, from the radial velocity curves. And as time goes by, the Doppler shifts will decrease. And if I stop the animation at this point, we're seeing that as the red star begins to be eclipsed by the blue star, the total combined intensity begins to dip, of course, because I'm losing the light from the red star. And so just looking at the depth of the dip that is being created when the difference between full intensity and intensity during the full eclipse of the red star by the blue star, this difference is precisely a measurement of B2. And of course, if I know the brightness of star number 2, then by subtraction, I know the brightness of star number 1. So I have a measurement independently of the brightnesses of the two stars just by looking at the light curve. Step number 1. I'm going to have to erase this because I'm going to annotate this diagram very heavily. Another thing we note is that at this point, when they're about to eclipse each other, the red star, star number 2, is moving precisely to our left with a speed v2, which presumably may be measured by Doppler shifts. And at the same time, star number 1 is moving to the right at his speed v1. And so the speed of relative motion is just v1 plus v2. And this tells us something, because what we're seeing is over here at this time, we're seeing the beginning of the eclipse right over here. And of course, if we let time pass, we'll see that as star number 2 is increasingly eclipsed by star number 1, the light curve dip deepens, and it reaches its maximum depth at this time right over here. And if we call this time interval t2, then we can describe what happened during this time interval. What happened during this time interval is that the combined motion of the two planets carried them through the diameter of star 2, from the point when star 2 was just touching the outside of star 1 with its left edge until it just disappeared around behind it. So v1 plus v2 times t2 is twice r2. If we measured the speeds using Doppler shift, we now have an independent measurement of the radius of star number 2. And of course, if I let the animation run a little bit more, then we can see that when the red star reemerges, I now have a measurement of the combined intensity again, and about this point I get maximal blue shift on the red star's spectral lines, maximum red shift on the blue star spectral lines. And when the next eclipse starts, first of all, the directions of the speeds are of course reversed, but I'll leave them there. Please do not get confused by this. But now I can measure a different time interval. Of course, the length of this time interval during which the dip develops is again the same length. It's the time that it takes the red star to move relative to the blue star, twice the red diameter. But if instead I start my clock now and measure the time it takes until the following happens, until the eclipse begins to be decreasing, until this point, this time interval over here is the time that it took the relative motion of the two stars to carry them through the diameter of the blue star. So v1 plus v2 times this interval t1 is just twice r1. So we have a measurement of the radii of the two stars, and at least their ratio if we don't have Doppler shift measurements. If we do have Doppler shift measurements, we can get the exact radii, but certainly we can get a ratio of the radii. We found the brightnesses of the two stars independently. We can also get an independent measure of the temperature. Notice that the dip created when star number 1, when the blue star is occluded, is deeper than the dip created when the red star is occluded. This has to do simply with the fact that the blue star is hotter. Notice we don't get a total eclipse of the blue star. It's not measuring its total luminosity. What I'm missing here is a disk out of the surface of the blue star equal to the size of the red star. What this means, of course, is that the reason this dip is deeper is because this corresponds to losing a disk with a temperature T1 to the fourth, and this corresponds to losing a disk with a temperature T2 to the fourth. The ratios of the depths of the two dips tell me about the ratio of the temperatures of the two stars to the fourth, and you can see that as I adjust the relative temperatures, I will find that this will the relative depth of the two dips will change when I set the temperatures equal. The dips are equal in depth. As long as the smaller star is cooler, the dip when it is obscured is less deep, and if I make the smaller star hotter, then the arrangement is reversed. So we can read lots of things off of this figure. I hope you'll play with the simulator. I should show you two other things if I can erase all my notations. One is that if the orbit happens to be elliptical, I can give it some eccentricity. And what happens then is that depending on the orientation of the ellipse, the two dips might not be symmetrically positioned within the orbit, within the period, because it might take the two stars. What we see is that this, in between this eclipse and this eclipse, falls perihelion. When the two stars are close together, they go fast. In between this eclipse and the following eclipse this way lies aphelion. That takes longer, so we can get a measure, but the asymmetry gives us a measure of the ellipticity, the eccentricity of the orbit. And furthermore, if we have stars whose radii are comparable, then of course, when the radii become close, we never get this flat region on the bottom because total eclipse occurs only for an instant. But even more fun, if as the stars combined radii become closer and closer to the radius, we get what we call a contact binary. A contact binary such that the stars are essentially touching each other. That's the situation I have here. What a contact binary does is it causes the flat region where we get constant full luminosity to disappear, because essentially the stars will eclipse each other and then immediately start the other eclipse, and we never get this constant period of full illumination. Lots and lots of information to be read off a light curve. The same applied to planets. I promised then that I would show it to you at some point. I hope this has been instructive. So eclipsing binaries are a rich source of information. In general, we can learn a lot from binaries. The most famous example of eclipsing binary is, of course, as we call it, Algol, or perhaps Algul, which is the ghoulish-looking star in Perseus that dims for a few hours every few days, because it turns out it's an eclipsing binary. As we'll see later, there is yet more information that we can extract from binaries. Binary stars, as I like to call them, are a star with a built-in probe, and we can learn a lot about both members of the pair because there's something for them to interact with. So we'll come to binary stars again and again as the class goes on. For now, let's observe that our friend Alpha Corona Borealis happens to be a double-line eclipsing binary with a period of about 17.4 days, and we can do the Doppler measurements. Again, I quote in the credit section the paper from which I lifted these data, and it would be fun to go and read the paper, and you can see that you can learn a lot from that. Doppler measurements give me the radial velocities of the two stars, and I give here the speeds as we measure them. I plug into our formula for the masses of the two members of the binary. Of course, this was our formula for M1. Replacing every 1 here with a 2, I get the formula for M2, and I predict that Alpha is a pair of stars, one with a mass 3 times the solar mass, one with a mass approximately a solar mass. I can compare this with my spectral measurements. Since it's a double-line binary, I see the spectra of both stars. Indeed, we talked about Alpha Corona Borealis A last time. We said there was an A-type star. That mass of 3 solar masses and a radius, we said then, of about 3 solar radii is about right for an A star. Alpha Corona Borealis B turns out to be G5V, which makes it a little bit cooler than the star. Its radius should, than the sun, I mean. Its radius should perhaps be a little smaller, but another main sequence star. You can read about the light curve fits in the paper that I quote. You can also see how life is never quite as simple as what I presented in this idealized scenario. In particular, for example, the eccentricity of the orbit is very high, so our circular orbit calculation is bound to be a little bit inaccurate. In fact, from the paper, including both the eclipse data and the radial velocity data, the best estimate they find is about 2.6 solar masses for A and 0.9 solar masses for Alpha Corona Borealis B, a radius of about 3. We got that right, because temperature and radius don't care for radial measurements. So indeed, the radius of Alpha Corona Borealis A is 3 solar radii, and of the secondary 0.9. The temperature we had right for the primary. The secondary is about the solar temperature, and the little ratio of luminosities, the luminosity in units of the solar luminosity, is what you would expect from their spectral type. The beautiful thing is, yeah, these people did some very careful numerics, but we understand and can actually emulate at least the physical principles, if not all the details, that went into this calculation. I hope you appreciate how much you've learned.